right, so here we go with part 2 of section 5.4 of the fundamental theorem of calculus. What we're doing is we're evaluating definite integrals using anti-differentiation. All right, so here we have another definite integral. Lower limit of integration is 1, upper limit of integration is 4. The function we're integrating is 3 root x. Now, I can't integrate that as it sits because I don't have a rule for square roots. So I'm going to rewrite this as 3 times x to the 1/2 dx, and now I can find an antiderivative because I have a rule for that. I can use that power rule, and so it's going to be 3 times, 1/2 plus 1 is 3/2, so 2/3. Okay, I don't know why it does that. X to the 3/2 evaluated from 1 to 4. Okay, this is going to clean up and just become a 2, so I have 2 times 4 to the 3/2, that's the upper limit of integration, minus, right, now we need to do the lower limit of integration, 2 times 1 to the 3/2. All right, let's see, I'm going to factor out that 2, just call this 2 times, 4 to the 3/2. Let's see, the 2 in the denominator means square root, 3 in the numerator means cube, so square root of 4 is 2, 2 cubed is 8. Minus 1, 8 minus 1 is 7, 2 times 7, 14. And so the value of this definite integral is 14. Given that this is a wholly positive function on the interval from 1 to 4, we could make the argument that this is area under the curve, area bounded by the curve. Right? All right, so here we go. Another problem. My job, once again, is to do the same thing. Again, I need to do an integral. I have a lower limit of integration, upper limit of integration of function. Find an antiderivative. The antiderivative of secant squared is tangent. So this is going to become the tangent of x evaluated from 0 to pi over 4. Okay. Evaluating at the upper limit gives me the tangent of pi over 4 minus the tangent of 0. The tangent of pi over 4 is 1. Tangent of 0 is 0. 1 minus 0, I'll do the heavy lifting here. That's 1. All right. Value the definite integral. I'm just evaluating definite integrals. That's all I'm doing. All right. Let's see. I've done this one before. Not as a definite integral with a lower limit and upper limit, but I've done this one before, so I know what to do with this 1 over x that's hiding in there. That's going to become the natural log of the absolute value of x, evaluated from 3 to 6. So that's going to become the natural log of 6 minus the natural log of 3, which is the natural log of 2. And so there's my final answer. Now I know there's at least one person going, whoa, what happened between that step and this step? Remember the rules for logarithms, that this subtraction can be rewritten as division, so this became the natural log of 6 divided by 3. 6 divided by 3 is our 2 right there. Okay. All right. Oh, I got a problem here. I've got a quotient as my function. Whoa. I got 2 problems here. One of them is there's a typo. So that needs to be fixed. That should not be dc, that should be dv. I'm going to fix that on your version. All right, that's now fixed on yours, so you'll see a dv there, not a dc. All right, so I can't deal with this as it is because of the silly fraction, but I'm going to do the same trick that I learned way back when doing derivatives, where I'm going to rewrite my integral. Since my denominator is a monomial, a single term, I'm just going to rip it apart and then rewrite it because I can. All right, so let me get rid of all this extra penmanship that doesn't need to be here. There are times when I don't know why it doesn't work as well as it should to erase. All right, so first things first. It's still a definite integral. It's still from 1 to 2. First one, when I rip it apart, that's going to give me a 1 over v. The second term, when I rip it apart, it's going to give me a 3v squared. And this is all dv. All right. You'll notice that I did not remove this because I haven't integrated yet. So the operator is still there to tell me what to do because I haven't done it yet. All right, so that's going to give me the natural log of v plus v cubed. and that all needs to evaluate from 1 to 2. Now you might be wondering why I did not use absolute values here. Is because I was looking a step or two ahead and saw that the limits of integration are positive numbers, so I don't need to worry about taking the antiderivative and having it be an issue with negative numbers. So I'm just going to deal with it as it is. All right, so now I am going to evaluate this one, but I'm going to evaluate this one in a slightly different way. I'm going to make use of this addition symbol here. And so what I'm going to do is I'm just going to evaluate this one at upper minus lower and this one at upper minus lower, and then add those two results. So essentially it's going to look like this. The natural log of 2 minus the natural log of 1 plus 2 cubed minus 1 cubed. Now you might be wondering why I would do this. Well, it just makes things happen a little faster for me. Okay? Natural log of 1 is 0, so this just becomes natural log of 2 plus 7. 2 cubed is 8, 1 cubed is 1, 8 minus 1, 7, and I'm done. Okay? Now, you can always do this at addition and subtraction symbols. You can always break apart that evaluation of this. And sometimes for something like this, where one term is a logarithm and one term is a polynomial, it ends up making the evaluation kind of faster because essentially what it does is it groups like terms for us. Since we have two totally different things going on here, logarithms and cubing, let's put the cubes together, let's put the logs together and make math happen more quickly for us. Right? So I'm evaluating these things. Right? Now, let's take a look at an application of this evaluation. This application is called the mean value theorem. The mean value theorem for integrals states that if we think of life, I guess we'll say it like that, if we think of integration in terms of area, then the area under a curve could be set equal to a similar shaped rectangle. Okay? All right, so if we look at this function that I've got over here, and I don't think I did a very good job of explaining it just then, so let's try again. I have a function y equals f of x. If I asked you to evaluate the definite integral of that function f of x dx from a to b, you would get all this purple area and all this blue area up there added together, and that would be the value of that definite integral. But what if we took this blue area up here and smushed it down and took this red piece over here and pushed it up? Could I find a rectangle that had the exact same value in terms of area as that curve does from A to B? You'll notice that we don't change the horizontal A to B. Right? And so what the mean value theorem says is that if you have a continuous function on a closed interval, that you can always do this, that you can always find some value that's going to turn this into a rectangle that would have the same area. And that value, that height for this rectangle here, this f of c, right, that is referred to as the mean value or the average value. Now, the word mean that we're using here is the statistical definition of the word mean. And in stats, the word mean means the average, the arithmetic average, because there's several different averages. There's arithmetic average, harmonic average, there's geometric averages. There's a whole bunch of different averages out there, but the arithmetic average, the one you think of when you say the word average, technically you should call that the mean, right? Which is why this is called the mean value rather than the average value. So the mean value theorem, right? And so basically what it states is that the mean value theorem for integrals says that if you have a function that is continuous on a closed interval, then there is a number c somewhere on that interval that's going to give you the height that you could use to find the rectangle that would have the same area. Or, and there's a couple different ways that this theorem is sometimes introduced, with a little bit of algebra, could I take this and modify this and say that 1 divided by b minus a times the integral from a to b of f of x dx is equal to f of c. Just take and divide both sides by that quantity. Okay? And you'll sometimes see it represented this way. Right? This would be the second representation here. This one would be the way that you'd want to represent it if your job was to figure out what c is. Because everything on the left can be calculated directly from the knowns, and then we could use it to find that unknown c on the right. Right? All right, now, one of the things to keep in mind is even though the picture that I drew has this function being positive on this entire interval, there's nothing in the definition that says it needs to be positive. So this could be a function that is sometimes above and sometimes below. It could be a function that's always below. It could be a function that's always above the x-axis. It doesn't matter. That value c will still exist because we could always turn this into a rectangle. It just might be that the height, and I'm using that term very loosely here, of the rectangle might need to be negative if more of the curve was below than above. Right? The mean value theorem for integrals. So basically, what's the math behind this? Well, what it's saying is that you can always find the average value of a function on an interval if it is a continuous function. You can always find the average value. So if that function f of x represented a population of something over a time interval a to b, then f of c would be the average population for that time interval. If the function f of x represented the speed of an object on a time interval from a to b, then f of c would be the average speed or average velocity, depending on what f of x represents. Okay? So we use this idea, we use this concept anytime that we want to find the average of something that is changing all the time. So if we want to find the average depth of the water, well, find me a function that measures the depth of the water, like the tides. Right? And so if f of x represented the height of the tide on some time interval a to b, then f of c would be the average height of the water, or the average tide depth. So what we're looking at here is we're looking at a function that finds an average. Okay? All right, so let's do our first example. Find the value c from the MVT, the mean value theorem, that's going to work for the function f of x equals x cubed on that closed interval 0 to 2. So I'm going to make a quick and dirty sketch of this thing. There's our f of x. Here's our interval 0 to 2. That's our area. We want to find some value f of c that's going to give us that mean value, that area, so that when you find the area of the rectangle here, it'll be the same as the area of the integral. Right? So first things first, I'm just going to rewrite the mean value theorem. The mean value theorem says that the integral from a to b of f of x dx, since we have a continuous function on a closed interval, will be equal to some f of c, a height times the width, the b minus a. Now I'm going to rewrite that, putting in all the values and the functions. Okay. Now the one thing over there that might be causing people trouble is what is this? Right? That is the function f evaluated at some unknown value c. The function f is the cubing function. At c, that would be c cubed. Right? Further evaluation. Left-hand side over here, I need to find the antiderivative x cubed. That's going to be 1/4 x to the 4th, evaluated from 0 to 2, is equal to 2c cubed. Right? Left-hand side, evaluating further. Right? I have 1/4 times 2 to the 4th minus 1/4 times 0 to the 4th is equal to 2c cubed. 2 to the fourth is what? 16. 16 divided by 4 is 4. So I get that 4 is equal to 2c cubed, or that c cubed is equal to 2, which means that c is equal to the cube root of 2. So this value c that satisfies the mean value theorem for integrals for the function f of x equals x cubed on the interval 0 to 2 is the cube root of 2. Or a different way to say that is, right? A different way to say that is that the average value of the function x cubed on the interval 0 to 2 is 2. Not the cube root of 2, 2. Right? F of c is the average value, the mean value. If c is 2, the cube root of 2, then what is the cube root of 2 put into the function f? That's 2. So the average value is 2. So be careful with these questions, because the value c is the cube root of 2, but the average value of the function is f of c, which is 2. So do you see what I'm saying there? What question is asked is going to depend on how you give them the answer. The value c that satisfies the mean value theorem is the cube root of 2. But the average value of the function, that's a y value, is actually 2. And how did I get that? I took that c and plugged it into the function f of x. And that's what gave me my 2, the average value of the function. All right, one more, and then we'll end this video and take a look at the next one. Okay? Same thing, I want to find the value c that satisfies the mean value theorem for the function square root of x on the interval 4 to 9. Okay? I'm new at this, so I'm just going to write out the mean value theorem first. The mean value theorem for integrals says that the integral from a to b of some function f of x dx is equal to f of c times the b minus a. Okay, replacing all the a's and b's in f of x is with the known values, 4 to 9, of the square root of x dx is equal to the square root of c times 9 minus 4. Okay? This is my little f, so I need to find an antiderivative. Okay? So I'm thinking of this as x to the 1/2 in my head, so I know that the antiderivative is 2/3 x to the 3/2. I need to evaluate that from 4 to 9, is equal to 5 root c. 9 minus 4 is 5. Evaluating further, I'm going to have 2/3 times 9 to the 3/2 minus 2/3 times 4 to the 3/2 is equal to 5 root c. Okay. 9 to the 3/2, the square root of 9 is 3. 3 cubed is what? 3 times 3 times 3, 27. Okay, so 18 minus, let's see, the square root 4, 8. 8 minus 16/3. Square root of 4 is 2. Square root of 4 is 2. 2 cubed is 8. 8 times 2/3 is 16/3. Okay. Now I have to do 18 less 16/3. So 18 as thirds is 54/3. So I'm going to get 54 minus 16/3 is equal to 5 square root c. Okay. Dragging this over here to the right, I'm just going to, oops, I wanted a highlighter. Separate this out. I'm going to drag this up there. I'm going to try that again. I'm going to drag this up there. There we go. Finally got it. 54 less 16 is what? 38. And so I've got 38/3 is equal to 5 root c. Divide both sides by 5. I get 38/15 is equal to the square root of c. Square both sides. I get that c is equal to 38/15 squared. Okay, I'm going to need a calculator for that. 38/15 squared is 1444 over 225. 1,444 divided by 2,225, which is approximately 6.42. It's 6.417 repeating, but 6.42-ish, which is nicely between 4 and 9. Okay? All right, so the average value of the function on the interval can be found when c is equal to 1,444 over 225, or a different way to say it would be to say that the average value of the function is 38/15. And where did that come from? Oh yeah, I took c, plugged c back into the original function, took the square root, which, if you're one of those people, is sitting right there. The square root of 1,444 over 225 is 38/15. So depending on which question is asked, c is 1,444 over 225, or the average value of the function, the square root of x, on the interval from 4 to 9 is 38/15. Okay? So I'm finding the value c. I'm going to end this video here. We're already 20 minutes, so we'll make a third one for this.